Hi everyone, I'm Dennis Gravert, and I would like to wrap up the second part of Key Concept, Unit 1, Part 1. Let's go to that now. Here it is. Okay, and so in our first video on Key Concept, Unit 1, Part 1, we went over skeletal drawings and how to go from, go from a regular structure to the skeletal drawing. And we also took a skeletal drawing, went back to a regular drawing. We also refreshed our memory about how many times these atoms bond. Now, there's a nice fancy way of doing it back in general chemistry involving the noble gas electronic configuration. So this is really just a shortcut, not the right scientific way of explaining it, but it's a great shortcut. HONC, H-O-N-C, H stands for halides and hydrogen, bonding one time, oxygen twice, nitrogen 3 times, carbon 4 times. There are exceptions, but we won't see any today. We will in this course, however. But again, nice stable molecule, hydrogen, oxygen, nitrogen, carbon, and the halides tend to bond in this pattern. Okay, next on the key concept. We skipped it in the first video, was a definition of zwitterion. Zwitterion, that's simply a molecule that contains both a positive and a negative charge. Yeah, that's unusual, right? You would think, well, shouldn't the minus and the plus just cancel out? Well, nature, she makes all the rules and says that in this case, no, this is very stable, better than being neutral. So it's up to us as scientists to try and figure out why. And the first thing we did is just named it, put a label on it. Hey, look at this, zwitterion. It was the Germans who did it first. Zwit is related to the German word for the number 2, zwei, I think. So this literally means 2 ion, or 2 ions present in the molecule, a plus and a minus, an anion and a cation. The molecule specifically shown here is alanine. It's one of the amino acids found in proteins. So yeah, proteins are important. A lot of amino acids exist as zwitterions. So something we'll see from time to time. Next idea is curved arrows. Okay, so we need to finish. We need to spend some time on this as we finish up Key Concepts Part 1. Curved arrows. Okay, we first of all have normal arrows, right? So let's talk about arrows real quickly. That might be a reaction arrow. Hey, compound A changes to compound B. That's a complete reaction, one-way reaction. You might have equilibrium arrows, right? So sometimes A changes into B, but you know what? B can go back and change into A. The reaction goes forwards and backwards. And now we have something using a curved arrow. Okay, in this case, curved arrows are showing the flow of electrons. It might be helpful to think about it as electric current. I'll try and make some reference to that. Maybe that'll be helpful. But a curved arrow is just showing us how we move electrons in order to break an old bond and create some new bonds, right? So, you know, what is a bond? What we got here, we got a bond between carbon and oxygen. That's a pair of electrons, right? And so if you want to break this bond, you have to move this pair of electrons out from between the carbon and the oxygen. You have to move them away to break the bond. Or maybe you want to make a double bond somewhere. You have to bring in 2 electrons. 2 dots equals 1 line. 2 electrons, 2 shared electrons makes 1 covalent bond, right? So you have to move in some electrons to make bonds. And the curved arrows is going to show the flow. We're going to start with an old bond being broken. And we're going to move those electrons from that bond and make a new bond with it. And that's what the arrows are showing. So it's really important to emphasize curved arrows are showing motion of electrons. Okay. When are we going to use curved arrows? Well, there's two general cases. One is in resonance structures. Another one is in reaction mechanisms, sometimes just called mechanisms. All right. Let's review resonance structures before we move any further with the curved arrows. So let's try to think of an example of a molecule that possesses resonance structures, and I thought of the acetate ion. You might recall that from general chemistry. It's one of those polyatomic ions that you had to memorize. Acetate, it's still a good idea to have it memorized. We're going to keep using it in organic chemistry as well as a little bit of general chemistry. What are the chemical formulas for acetate? There's two that are commonly used. One's C2H3O2 minus. Acetate is an anion, a -1 charged ion. The other formula is CH3COO minus. Okay, there's other variations of these, but pick one. And now what I want to do is draw the Lewis dot structure. And it's kind of helpful to have both of these. So the whole molecule, acetate, has 2 carbons. This formula on the right actually tells us how they're connected together. The first carbon of the 2 is connected to 3 H's, and honk tells me hydrogen bonds 1 time, carbon bonds 4 times. So it must be a single bond that connects the CH3 piece to the carbon in the middle. This carbon in the middle is going to connect to an O and another O. So you might say, oh, is that a C to O to O? Maybe that's how it attaches together. And no, this oxygen's happy. It's making 2 bonds, but carbon is not. And if you try and give it double bonds here, yikes, this carbon is now making 5 bonds, and this oxygen is making 3. No, we gotta keep honking fresh in mind. We're after these ideal number of bonds. That'll help ensure we have a stable molecule. So you have to try and sort this out, and what you might come up with is, well, let's not have the oxygens in a row. Let's have carbon, which bonds 4 times. Maybe it's bonding to more than 2 atoms. Yeah, let's let it bond to 3. The carbon on the left, an oxygen up above, oxygen on the right. That's only 3 bonds to the carbon. Don't use another single bond because there's no more atoms. We used them all up. There's only 3 H's, got them. 2 C's, got them. 2 O's. So maybe we'll just insert a double bond here. Can't put it here, right? Because I give this carbon on the right too many bonds. Where's my eraser? Get rid of that bond. Goodbye. Can't go there. Nice. Okay. So I'm gonna guess it's gonna go up here. Now oxygen's happy, making 2 bonds. Carbon's happy, it's got 4. Carbon over here on the left has 4. Hydrogen has 1. It's all looking good except for this last one over here. You know what? That's okay. We still have to take care of this negative charge. And so it turns out that when atoms, at least these atoms, are not bonding normally, they probably have charge. Or another way of saying it, when these atoms bond normally, 4 bonds carbon, 2 bonds oxygen, they usually have 0 charge. They're neutral. And that's what makes them more stable, right? Nature likes neutrality. So we have an ion, though, is negatively charged, which means one of these atoms probably is not bonding normally, and I've decided in my structure it's going to be this oxygen on the right. It's still a good Lewis dot structure, so I need 8 dots around this oxygen. So let me give it 3 lone pairs. And then you might recall a formula for calculating formal charge. We're not going to review that right now. But it turns out when oxygen only has one covalent bond and 3 lone pairs, the oxygen possesses a formal -1 charge. And it's the only atom in the whole molecule that has charge, so the whole molecule has a net -1 charge. Hey, that explains the charge on acetone. Okay, let's finish out the Lewis dot structure. This oxygen's not happy. It only has access to 4 electrons. 1 line equals 2 dots. So I gotta give it an octet. There we go. Carbon has 4 lines to it. Each line is 2 dots. There's 8. This carbon has 4 lines. Hydrogen has 2 electrons. Everybody's happy. Good Lewis dot structure. Cool. Wait, I thought we were talking about resonance. Yeah, let's talk about resonance. How come it's the oxygen on the right that's negative? How come it couldn't be the oxygen up on top? It can be. So sometimes, you know what? No, let's do it this way. Sometimes you could draw the structure this way. Put the oxygen on top, connected through a single bond, and the oxygen on the right, connected through a double. And then if we want a good Lewis dot structure, this O on the right can only have 2 lone pairs because it's got a double bond, a total of 8 electrons. There's that octet rule. The oxygen up on top, though, only has 2 electrons right now, so it needs 6 more electrons or 3 lone pairs. This carbon has 4 lines, 8 electrons, it's good. This carbon's good too. All right, this oxygen is not bonding normally. It should have 2 bonds. It only has 1. So now this is the oxygen that has a net negative charge, a formal charge of -1. And then what we would say is that there's 2 possible structures. We would identify these as resonance structures, and we'd use another type of arrow, a resonance arrow. It is a single line with 2 arrows on either end. One way of interpreting this is that sometimes the acetate ion looks like the molecule on the left, sometimes it looks like the molecule on the right. And if you do some experiments and do some measurements on acetate, it turns out that's not an accurate summation of acetate. It's not sometimes the left one and sometimes the right. It's an average of the 2. In other words, instead of a double bond to oxygen sometimes and a single bond to oxygen sometimes, it's more like a 1.5 bond. That's what the measurements are telling us. So resonance structures really is a blending of the molecules. I had an instructor tell me, hey, if this molecule was blue and this structure was yellow, well, blue and yellow make green. So the whole molecule would just always be green. It wouldn't flash blue, then flash yellow, flash blue, then flash yellow. No, it's just always green. It's a mixture of the 2. And really not ever one or the other. Okay, enough about resonance structures. Hopefully that was a good review of how to draw them and so forth. Let's use a curved arrow with this. And what I want to do is I want to show how the electrons move in one structure to change, let's say, the left structure into the molecule on the right. So how did that happen? What set of electrons moved? Well, start with the carbon on the left maybe and realize, hey, there's 4 single bonds in both cases. None of those electrons moved. Hey, but there's a double bond that's vertical here, and now it's a single bond. And wait, there's a double bond that's horizontal here where it used to be single. It looks like one of these bonds just slid down. That's what it looks like. But is that really the case? Let's use some terms. What's the hybridization of this carbon? From the last video, we discovered that if an atom is making a double bond, it may be sp2 hybridized. Okay, so let's check here. There's a single bond here. Maybe we'll just call it sigma. There's another sigma here and another sigma. The double bond has one sigma and one pi. So this carbon actually has 3 single bonds. Well, yeah, if you have an sp2 hybridized atom, that came from an s, p, and a p. That would give you 3 sigma bonds, or say 3 single bonds, 3 orbitals that can each make a bond, or can each hold a lone pair. And then this 4th bond to carbon is the pi bond. So you have 3 sp3 orbital, 3 sp2 orbitals, and we have a pi bond. Okay, so the term I'm looking for here is, hey, the oxygen used to have a double, then a single, it lost its pi bond. Remember, the pi bond's the one that's on the top and bottom. It's more reactive than the single bond in the middle. Okay, what about the oxygen over here? It has 3 lone pairs, single bond. Later, there's 2 lone pairs, and a pi bond showed up. I was thinking initially that maybe I just move these 2 electrons down here. And if I draw that in, I just now have given the oxygen too many electrons. There's 10 electrons around here, not an octet. Where's my eraser? Making mistakes all over the place. That's okay. Use mistakes to learn. Learn from your mistakes. Let's flip this back up. Okay, so what's happening here? What's really going on is one of these lone pairs is becoming a pi bond. So I'm going to choose this lone pair. And what we're going to do is say, hey, these 2 electrons move down here between the carbon and the oxygen, and now they're being shared. Someone else might say, well, I got a lone pair on top, lone pair on top. There's a lone pair on the bottom, lone pair on the bottom. The lone pair on the right side is the one that moved. So yeah, that's fine. You could have chosen to start your curved arrow on this lone pair and moved it over to the carbon. You could even come from underneath. We're just showing the main idea. A lone pair moved off of oxygen and now became the pi bond. It completed a double bond. If by drawing that pi bond, that messed up the octet rule for oxygen, it also messes up the octet rule for carbon. So at the same time the lone pair comes down to make this double bond, you have to lose the pi bond up here. So what's going on here? This oxygen has 2 lone pairs, left and right. Whoops. Still has lone pairs left and right. But there's a new lone pair on top. So what happened is a pi bond, I'm going to choose this left side to be the pi bond, actually moved up onto oxygen. There we go. We've drawn 2 curved arrows, and that explains the motion of the electrons that changes the left structure into the right structure. You can go the other direction too. We usually don't. We usually think of going from left to right, like reactants from the products. But if you so choose, you could say, hey, over here, what's going on? Maybe I should use a different color. Let's use green there. How are we going to move these electrons to get to this structure? Well, we'll just undo things. This pair of electrons turns into the pi bond, and this pi bond turns into a lone pair. Cool. All right, that's one illustration of how we use curved arrows to show, to illustrate how resonance structures kind of switch between their 2 structures. Another way we commonly use curved arrows in organic chemistry is to explain reaction mechanisms. So I don't know if you remember reaction mechanisms, but in general chemistry, you're supposed to talk about it during the topic of kinetics. So when we talked about rates of reactions, we also talked about reaction mechanisms. So here's a very common one you may have seen. I'm hoping you have. And if you haven't, that's okay. Let's kind of go over it. It has been a while since Gen Chem. Okay, here's the idea. We got this observation that if we have this white crystal of silver chloride, it's a solid, crystals, yep. You can dissolve it if you add concentrated ammonia, NH3. And that's what's in this graduated cylinder here, some concentrated ammonia being poured in. And it doesn't show it stirring. It actually takes a few, takes a little bit of time. But yeah, all the solid disappeared. It all dissolved away. How'd that happen? Well, here's the proposed mechanism, the step-by-step procedure and how it occurred. Down here, before I get too far ahead of myself, is the overall reaction. You take some silver chloride as a solid, add in 2 equivalents, 2 moles of ammonia for every 1 mole of silver chloride, and you get a complex ion that's soluble. Weird complex ion. There, 2 ammonia molecules are now stuck to a silver cation, and you got the chloride ion all floating around by itself, and it's all dissolved. Okay, how does this happen? Well, the proposed mechanism, the step-by-step process, is first silver chloride is generally insoluble, but there's an equilibrium where a little bit of solid can spontaneously dissolve. And you know it's reversible. Reversible. These 2 ions, the cation and the anion, can actually stick back on the crystal, or it can start a new crystal. It can go back between solid and aqueous. Looking at the equilibrium constant with a negative exponent tells us, ooh, the reactants are favored. So this doesn't happen too much, but a little bit does. And so there's a few silver ions in here, a few chloride ions in here in solution. And when you add the ammonia, the ammonia can react with the silver. They stick together, 2 species. One's a cation, the other one's a molecule, a neutral molecule. They stick together to form this complex ion. And this complex ion is shown down here again. It's going to react a second time. So in the 3rd step, a molecule of ammonia reacts, connects, and you get the final product, this stable complex ion. And that's the process, that step-by-step mechanism. Cool, in general chemistry, we're fine with that. Yeah, let's move on. The organic chemist, though, we want a little more detail. It's like, okay, this is cool, but show me the flow of electrons. What bonds broke and which bonds were made that go from top to bottom? Okay, so technically speaking, this salt, this ionic compound, just separated, right? The cation and the anion, there's some collision with the water molecules, or there's a heat energy was added so that the vibration of the cation and anion just made them fall apart. There was no flow of electrons. This AgCl consists of a silver cation stuck to a chloride anion. And somehow they're separated from each other. No electrons are moved. Just the ions themselves physically separated. No curved arrow. So that's one of the features of ionic bonding. Okay, second reaction here. We have NH3 connecting somehow to silver. So I wrote it over here. And to figure out where the curved arrow is, we have to figure out where the bonds are. So let's look at this a little bit more detail by reviewing Lewis acids and bases. And I probably should start with regular acids. What is this, the Bronsted-Lowry definition, I think? Acids, the old definition, Bronsted-Lowry. Acids are H+ donors. Bases are H+ acceptors. All right, and here's your typical neutralization reaction. You got H+ coming from an acid. Bases usually provide hydroxide ions. And then the cation and the anion neutralize each other. You form water. Super stable, nice reaction, exothermic, yeah, acid-base chemistry. You can also focus not on the motion of H+'s, right? So an acid In an acid molecule, the H plus leaves, moves away. The base, the H plus comes in, comes toward. Curved arrows talks about moving electrons. So let's redefine acids in terms of where the electrons are moving, how they are moving. In this case, we start with, I like starting with the Lewis base. Lewis bases have lone pairs, and they donate them to make a bond with the acid, the Lewis acid. The Lewis acid is just going to attach to those lone pairs. So if we go back to this neutralization reaction, which I wrote down here, and I'll ask you who has the lone pair, H plus or OH minus? H plus. Any electrons at all there? Hydrogen is element number 1. Started with 1 electron, but it lost it. It lost its one and only electron. Yeah, H plus is a naked proton. No lone pairs there. That can't be the base. It has no electrons to donate. Yeah, it's hydroxide ion. So let's actually draw the Lewis dot structure of hydroxide ion. There we go. H bonds 1 time. Oxygen's supposed to bond twice, but again, it's negatively charged. So somebody's not bonding normally. Oxygen wants 2 bonds. Nope, sorry, you only get 1. So you carried a formal -1 charge. It has 3 lone pairs and a covalent bond, so it still satisfies the octet rule. H plus, you don't have any electrons. There's your Lewis dot structure, just H plus. A simple proton. And then we're going to make a water molecule. I'll put the new hydrogen on the bottom. Okay, there's a Lewis dot structure of water. All right, so what changed? Where was the flow of electrons? Lewis base is using this lone pair. No, it's not. Using this lone pair, sorry, the one on the bottom, to attach H plus. So the H plus is accepting this lone pair. Hydroxide ion is giving it or lending it out to H plus. It's donating it. And the flow of electrons is from the lone pair to the H. The electrons are moving. They used to belong solely to the oxygen, but now they're going outward and connecting the H plus and making a bond. And now these 2 dots become this line. These 2 electrons attached to the H, and now it's a bond forming water. Cool. So here's the main idea and mechanisms. One idea, one pattern is that you can start an arrow on a lone pair, and it can connect to another atom. I should have pointed out with our resonance structure because we saw that pattern there. I just didn't highlight it. So here we go. Here's the curved arrow starting on a lone pair and forming a bond. So I got the arrow pointing in between 2 atoms saying, hey, those electrons are going in between to make a bond. Over here, got the lone pair actually heading directly towards its atom to attach the H to the O. The other pattern is that you can start on a bond. So that's what we did here. We said, hey, these 2 electrons, start my arrow, are going to move up onto this atom. So we point to that atom. And that tells us 2 dots, sorry, 1 line becomes 2 dots up on top of the oxygen. Okay, I wanted to review regular acids and bases compared to Lewis acids, Lewis bases, and I think we got it here. The oxygen has a lone pair, Lewis base. Curved arrow says that one of these lone pairs is going to be used to make a covalent bond to the H plus, the Lewis acid. That's actually what's happening over here in both of these reactions. How many lone pairs does silver have? Well, you have to look at the d orbitals and all that funky stuff. Let's not do that. Besides, it's got a plus charge. So like this H plus has a plus charge. It's probably our Lewis acid. This one's not negative like hydroxide's negative, but does ammonia have a lone pair? Oh yeah, it does. So nitrogen prefers 3 bonds. And it's got 3 H's attached to those bonds. Is that my Lewis dot structure? Octet rule. Nope. I still need a lone pair. There it is. So ammonia has a lone pair. It's my Lewis base. And what's going to happen is silver and ammonia stick together. The parentheses is telling us that all 3 H's remain attached to the nitrogen. And this whole thing, this ammonia molecule, is going to connect to the silver. Yeah, nitrogen is going to use its lone pair to connect, make a covalent bond, a coordinate covalent bond, if you remember that term from general chemistry. And it completes our complex ion. This is a covalently attached molecule. Even though it's ionic, it has a net plus charge here. Okay, and then we're going to do it again. The ammonia molecule still has a lone pair, and the second one is going to connect to the silver so that we have 2 ammonia molecules attached to silver, and that makes 1 single molecule of complex ion. There we go. Those are our curved arrows. Let me scroll over here real quick to make sure I didn't forget anything. I think we're good. Okay. Thanks so much. I'll see you later.